Hello, everyone. We're going to get going with this talk. So, come on stage. Yeah, let's go. Let's do it. So please give a round of applause for Liz Rice. She is a technology evangelist with a container security company called Aqua Security, and she's also a co-author of an O'Reilly book about Kubernetes security. And she's going to have a signing session later today out there, so come over. And she's going to be talking about eBPF Superpowers. And some of you might remember a few years back, Gregg from Netflix was doing his rounds saying that this is the Linux Superpowers. And hopefully today we'll learn how this landscape has changed over the years and how much more useful these things has become for people that use containers. So yeah, another round of applause and we'll get it going.
All right. Hi, everyone. Thank you for coming to this session about eBPF. So yeah, I work for Aqua and we're a container security company, but I'm really not going to talk about container security during this talk. I'm going to talk about this technology eBPF, or extended BPF, or extended Berkeley Packet Filter. Right. How many of you are using BPF in any form? I see a few hands. I put it to you that almost all of you are using some BPF, and I will explain why later. I hope I will remember to explain why later. Okay, so whether you know it or not, you're probably using some BPF, but you're almost certainly, if you didn't put your hand up, you're not taking advantage of all the cool things that you could possibly be doing with these eBPF superpowers. I'm hoping that by the end of this session, you'll understand something about how eBPF works, such that you feel that you could go out and write some eBPF programs yourselves. That's my goal. All right, so Andre already mentioned Gregg from Netflix, and I think he was the first person to use the word superpowers in relation to eBPF. Superpowers sounds really cool and really exciting, doesn't tell us very much about what it actually does. There's another great quote from Brendan that I quite like, I think does encapsulate things, where he says, eBPF does to Linux what JavaScript does to HTML. So if JavaScript makes your web pages dynamically programmable, eBPF lets you make the Linux kernel programmable. This is a black belt talk, so I am going to go I'm going to assume that you know things like what Userspace is and Linux and kernel space is, and I'm going to assume that you know that the interface between those two things is, or one of the big interfaces between those is syscalls. So with eBPF, we can run code, arbitrary code, programs that we write ourselves in the kernel, but without having to write kernel modules, without having to build our own kernels. So if we're in Userspace and we have a program and we're going to somehow get that program to run in the kernel, there's probably a syscall involved, right? And yeah, there is. There is a syscall called BPF, and the man page for BPF tells us lots of cool and interesting things about BPF and how it works. There is a BPF system call, but it performs a range of operations. There are lots of different subcommands to this system call. We're talking about programs. These programs have to be safe to run in the kernel. We're also going to see how BPF running in the kernel uses some helper functions and data structures called eBPF maps. Those highlighted things are pretty much the agenda for what I want to cover in this talk. So we should, by the end of this talk, understand a little bit about what you can do with BPF, what these programs are, how you use the BPF system call to run these programs, a little bit about verification, and a little bit about these data structures and in-kernel helper functions. Moving on down the man page, we find that these BPF programs can be written in C. But it's not the full language of C. You are limited in what you're allowed to do. And that C is going to get compiled into a BPF bytecode. So this is instructions that can run inside what's called a BPF virtual machine. Now, back in the day, I used to write quite a lot of code in C. So when I saw this is fine. I'm pretty chill about writing some C code. I can remember where the semicolon key is. It's going to be fine. I wasn't too familiar with what Clang is, so we'll just look up Clang. Clang is part of a project called LLVM, which is a collection of modern compilers and toolchain projects. They go to great lengths to explain that LLVM is not an acronym. I don't know how they came up with the name, or what maybe they just pulled 4 tiles out of a Scrabble game. Somehow they came up with LLVM. And Clang is the compiler, the C compiler, inside that collection of projects. Okay, so we're going to have this C code. We're going to write a program in C. Clang and LLVM are going to convert that into this BPF bytecode, so instructions in a kind of BPF language. And then moving on down the man page, we learn that the kernel is going to take that bytecode and compile it, convert the bytecode into native machine code instructions for your chipset. I just mention that because you kind of hear about this just-in-time compiler, which is worth mentioning. Okay, so I want to write hello world in BPF. How do I go about doing that? I'm going to have to write some C code, and one thing that I do remember from my kind of days of writing C is how painful it can be to install compilers and install toolchains. So that's kind of scary, but fortunately, there is a project called BCC that takes away the pain of that. Makes BPF programs easier to write. That sounds good. It wraps the LLVM components that we're going to need to build our eBPF programs, and it's going to give us some nice front-end kind of language wrappers in languages like Python that are easy to write. It's worth bearing in mind we're writing some C code that's going to turn into BPF, and that's going to run in the kernel. We're also going to have to write some Userspace code to, at a minimum, use the BPF syscall to get that BPF code into the kernel. We might also want to write something in Userspace to interact with that BPF program somehow. So the Userspace code we're going to write today, I'm going to use Python, and the kernel code we're going to write in C. Okay, I think it's about time that we start writing some code. So I'm going to do Python, but I'm going to have to declare what the C program is that I want to run. So you just basically have a string with the C code that we want. And I'm going to have a function called hello, because it's hello world. I'm not going to use the parameter that it takes. And I am going to use a in-kernel helper function, which allows us to output a trace. Like a trace text. So I might say, hello, DockerCon. And we need a semicolon. And we're going to return 0. So this is the function called hello that I want to get running inside the BPF virtual machine. And BCC makes it very easy for me to get that program into the kernel. I just have to say, here's my program, passing in the string that defines my C code. Something has to make this code run. Something has to, I need to say what it is that I want to trigger this hello function to be run. And for the purposes of this demo, I want it to run whenever the system call clone is run. Clone is what happens when you create a new process, and it's really easy for me to just run a program to create a new process. So I'm going to attach it using what's called a K-probe. We'll cover this a little bit later, but a K-probe is basically an event that happens when you run a function in the kernel. And my event is going to be the clone system call. And when that happens, I want to run this hello function. The one last thing I need to do is, from Userspace, get this trace output and display it. And BCC gives me a nice function to do that with. OK, let's see whether I've done it right. Hello world. Doesn't like something. Oh, I have to import from BCC import BPF. See, it's all live. OK, hasn't complained about anything, and that makes me feel fairly confident that my BPF program is now running. And if I run something, I'll just use who am I. That's going to create a new process. That causes clone to be executed, and that causes my hello world to happen, and that's very cool. We get my trace text that I specified. We also get some other fields kind of by default, like the name of the process that spawned that system call and its ID, and some flags and a timestamp. All right, so every time I create a new process, that's going to get triggered. Now let's find out what's happening underneath the covers at a syscall level by using strace. And I'm not going to trace out every single syscall. I have a selection that I think are interesting. Lots of stuff happens. There are lots and lots of file openings happening, and that's not a surprise because we're running Python code, which is interpreted, so we've got to read in the files containing that code. And we're compiling some C, so we can see things like header files being opened, or at least looked for, as part of this process. But things start getting really interesting around about here, where we see our first BPF system call. You remember it said there are various operations, and in this case, the operation is prog load. This is loading our program into the kernel. Then a selection of things, there's a couple of attempts to look for files that don't exist, and then we get some interesting system calls that clearly relate to attaching the K-probe. We can see K-probe events, and that sysclone name that we came up with. And we can see some ioctls doing things about setting BPF and enabling. So pretty clear that those are the system calls that relate to attaching my program to some kind of an event. And then we see our Userspace code calling open on this file here, and that's the tracing. So when the kernel creates some tracing output, it puts it there, and Userspace can read it out from there. And if I trigger a clone again, we can see Userspace can read that text and then write it to file descriptor 1, which is stood out, which is the screen. So we can see our first BPF system call, and we can see attachment, and we can see the trace. We can kind of see how that tracing is working through that file descriptor in that location. Oh, I didn't show you this lovely diagram, which was about how BCC is giving you this nice front-end code. It's giving you the encapsulating the compiler components you need, and it's making it really easy to write you don't have to write the system calls directly in most cases. It's kind of giving you convenience functions to do that for you. But as we've seen, BPF was being called under the covers. All right. We saw some system calls related to attaching the program to an event. And I used a K-probe, but there are lots and lots of other types of events that you can associate programs with. So there's K-probes and also K-ret probes, which is when the probe is when you start a function, and the ret probe is when it returns from the function in the kernel. And there's a user space equivalent called U-probes. So you could be attaching BPF events to your application functions. You can also have arbitrary user-defined trace points, pretty much wherever you want. You can trigger BPF on network packets being received. You can have them triggered by perf events. There's a whole ton of different places within a Linux system that can trigger BPF programs to run. BCC makes it pretty easy to attach the attach the program to a particular type of event. I did it explicitly with that attach kprobe call, but you can actually do it implicitly by just naming your functions. I think you can probably see how that function name correlates to a kprobe related to the system call clone. So that's the kind of classic hello world written in a slightly different way. Okay, we saw the helper function trace print k writing to that file location. And there's only one of those locations. So that's not going to be much good to us if we want to have multiple BPF programs, or if we have multiple user space components interacting. We don't want everything sort of bottlenecking through one file descriptor. So if we want to exchange information between user space and the kernel, this is just there for kind of debugging purposes. What you're really going to use is these data structures called eBPF maps. The man page tells us about that. Maps they're capable of storing kind of generic data. They're all maps, though. They all have a key that points to, or a set of keys that point to elements of data. And the elements could have different types, and there's a whole slew of different types of data that you can store in these maps. And they can be accessed from both the kernel side using helper functions and from user space using the BPF syscall. I slightly simplified something that was happening earlier. I talked about using LLVM and Clang to create the BPF bytecode. If we dive into that very slightly more, a little bit more detail, you're actually getting a standard ELF format file that defines the instructions, the BPF instructions, and it also defines the data structures, these maps. It's a regular ELF object file. So once we've got that object file, Userspace uses BPF to pass that into the kernel. We already saw prog load happening, and the maps get created using another subcommand of BPF called map create. When the program gets loaded into the kernel, that's when it gets verified, and if all is okay, it'll get passed into the BPF virtual machine ready to run. We saw the system calls that get used to attach a BPF program to some kind of event. And then we have the option to use BPF with some more subcommands to access data in the maps that we might have created. So it's a map. So the system calls let you do things like look up the element for a particular key, or traverse through the keys with this get next key. And you can both read and update and delete data from the user space side as well as from the kernel side. On the kernel side, those kind of manipulations are happening with helper functions. BCC makes it super easy, though. We don't really have to get into the detail of those helper functions because BCC gives us a whole bunch of kind of higher level wrappers to make it easy. Let me show you. Okay, so I am going to have a hash table. Oops. And I'm going to call it syscalls. And what I'm going to do is, instead of having a trace line output every time I call syscall, I'll have a counter that increments every time I call syscall, or every time the clone syscall gets triggered. Okay, so I'm not going to do this anymore, but I'm going to have a counter, and I'm going to start that counter at 0. I need a key for the map, and I'm only going to, at this point, have a map for one system call. I'm only going to be tracking clone system calls. But you could imagine extending this to track other system calls as well. So I'm going to use 56, which happens to be the opcode for clone, to identify, that's the key to identify the counter for clone. I'm also going to need a pointer, which I'll call P. Okay. So I can look up the current value of associated with a key. Under the covers, that is translated into a kernel helper function, but this is kind of BCC's version of. That's going to return me a pointer, and I have to check that the pointer is not null before I can dereference it. And then this function is going to be called every time I have the clone system call, so I'm going to increment my counter. Have I missed any semicolons yet? Shout if I do. And finally, I'm going to update the map, the elements at that key location with the new value of the counter. So that's the kernel side taken care of. And then in Userspace land, that trace print that I just deleted, that kind of blocks and continuously reads from the trace location. But accessing BPF maps is non-blocking, so I need to loop. And I don't want to hard loop, so I'm going to sleep for a few seconds. And then accessing the items in the map is as simple as... By the way, is this all big enough and high enough for you to read? Can you see okay? Good. I should have asked that much earlier. All right. So we can just iterate through all the key values in the map as simply as that, and we'll just print out any keys and values that we find. Now recall, we've only got one key because we're only tracking one system call, so I'm only ever expecting there to be 0 or 1 entries. 0 before we ever have any. Before we hit the first clone syscall, there will be nothing in our map. Okay. Oh, I need to import sleep, don't I? Okay, let's try that. Call the old one. Yeah. Hasn't complained, it's a good sign. And then if I start a new process, we start seeing the counter. And now we'll start seeing this every 3 seconds, because every time it will loop out and give us the current value. And if I run a few more processes, we'll have clone run a few more times, and we'll see the counter incrementing as we go. OK, that seems to work. Let's have a look at what's happening underneath. So I'm going to use my the same strace as before. A lot of it is very similar. There's our program loading call, but this time we also have a BPF syscall for creating the map. We do the same attachment process as before, and then we can start seeing these get next key calls. So this is my user space code trying to get a key from that eBPF map. It doesn't exist, there is no key until the first time we trigger that function. And now we should start seeing, I actually do that. Oh, I know. Yeah. So now we should start seeing the getting next key returning successfully, and then that means we can look up the element associated with that key and display that value. It tries to get the next key. There is no next key because there's only one entry in that map. Okay, so I think that kind of shows us the BPF system calls that we saw in the diagram earlier. It's all true, folks. I've kind of glossed over these helper functions, partly because BCC makes it you don't very often have to access them directly. But we did see the trace print k function earlier on. If you needed to, you could access these eBPF maps directly through a set of calls like map update element and map delete element, or LM rather. And you've also got a whole series of these helper functions for finding out about the current context of where this BPF program is running. So things like what the process ID is, what the current process name is. You can get things like the time out the system. All the kind of kernel side stuff is done through these helper functions. We also need to talk about verification. And one of the things that you can't do in the BPF code is look at memory directly. You actually have helper functions every time you want to look up a pointer in memory. In the kernel side, you have to use a helper function to do that. And that's just one of the rules that the verifier will check. So this verifier is there to ensure that your BPF program can't crash and that will actually run to completion. Crashing in the kernel is not a good thing. We all know that, right? So, for example, you're not allowed to loop because we need to know that the BPF program will exit. There's a limit on how many instructions. There are like 4,096 instructions, although you can chain programs together, so it's not insurmountable. And avoiding loops. Let's just see what happens if we do something that the verifier doesn't like. So, for example, I checked here that the pointer was not null before I dereferenced it, but it's perfectly valid C not to do that. We expect it to crash if the pointer is 0, but the compiler doesn't care about that in normal C circumstances. Now, if I try to run that, we get permission denied. We get it at the point where we're trying to load the program into the kernel. This is the BPF prog load call failing. And BCC is nice enough to give us these really nice hints which describe what it is that the verifier didn't like. And in this case, it's pretty clear because you must check. You have to explicitly check any pointer is non-null before you dereference it. And there's a really great blog post by NCC Group that talks about a whole load of experiences that they had writing BPF programs and kind of coercing and cajoling the verifier to work and let them do things that they felt should be allowed. And I just love this quote about the eBPF validator's muse is a fickle miscreant with a very short attention span. And that's a very well-written phrase. That blog post is definitely worth Googling and reading. There's some good stories in that. So at this point, we've seen kind of how BPF programs are constructed, and hopefully you have a pretty good view of how the kernel side looks and the user space side looks. What can we do with it? So we can create a lot of things. This is where Superpowers comes from. This diagram kind of illustrates, these are all example tools that have been written as part of the BCC project and its sister project, BPF Trace. And the first time I saw this diagram, I thought, what is this? What is all this? All the things around the outside are the names of these tools. And I think they're trying to illustrate how you can get observability into such a wide range of different components across the Linux system. So this BPF tool can be, it's not just one thing. You can use it for a lot of different things. You can observe behavior in networking, in CPU, in memory, in your applications. It's kind of limitless. We have seen that eBPF programs are restricted in the kind of C code that you can write, and you can't, for example, access any arbitrary memory. There are also limits to what you can do in terms of using BPF programs to control. So we've seen BPF being used to observe events. If you have BPF on packet filtering, which is its kind of heritage, right? You can look at a packet and make a decision about whether to pass it on or drop it. You can't do the same thing with function calls. You can't decide that based on what happened at a particular trace point that you want something different to happen in your application. So you can use BPF for a lot of observability, but it's quite hard to imagine using it for much in the way of security in the prevention sense right now. Except, I mentioned that I think you're all probably using BPF. And the reason why I think you're using BPF, not eBPF, but BPF, is seccomp. Who's heard of seccomp? Okay, a few more hands. So seccomp is a way of allowing or disallowing a set of system calls for a process. And Docker, by default, applies a seccomp profile every time you run a container. It's a very good default seccomp profile. And seccomp is using classic BPF to make decisions about whether or not a particular system call is allowed or not. But it has its limitations because it can only look at the arguments that were presented to the system call, and it can't sort of dereference those arguments if they're pointers. It also doesn't have the ability to kind of communicate with Userspace through maps, because one of the big differences between BPF and eBPF is maps. So although you're almost certainly using a seccomp profile every time you run a container, unless you explicitly turned it off, you are using it by default. It's a very powerful tool for making sure you don't run disallowed system calls. One of the things that's really nice in container security is the ability to limit executables that can run in your container. Now, that's something that you can do with commercial tools like Aqua, where you can say, I only want a certain set of whitelisted executables, for example, to run. You can't do that in seccomp because you can't dereference the arguments to. So, for example, you might say exec_ve, I know that a program is being run, but I can't find out enough about the program. There is a very cool project in development called Landlock that uses eBPF to enable this kind of thing. So it's like a super-powered seccomp. This is, people are not using this in production yet, but I think it will be a very interesting thing to watch in terms of container security based on eBPF. Because it's able to inspect kernel objects, so it can make really granular decisions about things like which executables to allow to run or not. And it can be configured on the fly from Userspace because it can use these eBPF maps. So I think that is definitely a technology that I'm certainly going to be keeping an eye on. This whole eBPF topic is huge and enormous. It kind of feels a bit like saying, if you know about eBPF, it sounds a bit like knowing about virtual machines. There are just so many different aspects to it. But if you want to look into it more, the IOVisor project is a very good place to start. It's the parent project for BCC, for BPF Trace, for things like Kube Control Trace, which lets you attach BPF programs to Kubernetes, or processes running under Kubernetes. So definitely check out IOVisor. Brendan Gregg's website, which I mentioned before, absolutely packed with really, really good posts and references and links to talks. It's really good. And then my final reference is an O'Reilly book that's in development by David Calavera and Lorenzo Fontana. If you have access to the O'Reilly Safari online thing, you can get an early preview of that book. And it dives into a lot of this level of detail. Okay, my last thing, and Andre did mention this earlier on, I co-authored this book about Kubernetes security. If you would like to get a copy of this book, or if you want to come and ask me difficult questions about eBPF that I can't answer here, then you can do that this afternoon. We're going to be handing out some books downstairs during the afternoon break next to the partner theatre, where simultaneously one of my colleagues will be talking about Aqua, if you wanted to learn more about that. So with that, I don't know, we might have a couple of minutes for questions. Have we got time? Is there? Oh, there are some hands up, yeah. Okay.
Will it work? Yes, it works.
Hey, so this is a fantastic feature, but we are here at DockerCon, so I have to ask, is there an easy way to leverage this Python package to say, hey, I want to apply this filter, but also I want to apply the additional filter of, can you give me everything running in this container? Can you say, I want to attach to this container like you would do with strace and follow?
Right. I don't know that you can do that directly in a general purpose way.
Okay.
Some of the data structures, I believe, are C group aware, so there might be some ways of attaching. And there are certainly some events that are C group related. So you might be able to kind of natively do it that way. And you obviously could do things like look at the current process ID, and if you're able to map the process ID to the container,
yeah,
that would be another way of doing it. I'm not aware, which does not mean that it doesn't exist. I'm not aware of a very simple way of doing that, but that would be a really great thing to build.
Because I'm sure going to go home and use this for debug purposes all the time. So
yeah,
thanks.
Yeah, actually, I think everybody should go away and write hello world, and then go and write a container-aware observability tool. There you go, that's a challenge for you. I think there was a question up the front here.
Hi, is there a way to load bytecode using BCC instead of the C code?
Sorry, can you repeat that again?
Is there a way to load the bytecode, the CLang compiled bytecode, using the BCC instead of the C code that you loaded?
So can you see the bytecode?
No,
yeah.
Not seeing. Can we load it using the BCC instead of the C code? So you have within the codes that hello program, right?
I'm actually struggling to kind of hear you, unfortunately.
Sorry.
You do get, I shall say some things that may or may not answer your question. So BCC has some debugging capabilities, and it will do things like tell you a kind of readable format of the bytecode. You also get the object file, so you've got the ELF file.
Okay.
You could output that, and then if you inspect the ELF file with like NM, like any other ELF file, you can see the bytecode in that. Mm-hmm. Does that?
Yeah, can I load the pre-compiled bytecode using BCC? That's my question.
Okay. Now that's actually quite interesting. When you run BCC, you are compiling the code live, sort of on the fly, and you have to have matching kind of kernel headers that match your current system. Mm-hmm. I read a blog post about somebody who was trying to pre-compile binary, kind of the whole thing, so like the Userspace, the BPF, and install the whole thing. My recollection was that, yeah, you had to have matching kernel headers, your headers when you compile the C code have to match the target platform. So I will try and find the blog post and tweet it out, because I think that is what you're talking about, but it is quite limited in terms of, you couldn't build a binary and run it on any, it wouldn't be portable to any, even the same chipset architecture, because it's got to be the right version of the kernel.
Okay. The reason I'm asking is because in the embedded platforms, we don't have the C-lang, compiling and running the C-lang on the target because of memory limitations. So I'm just wondering if there a way to load the bytecode using, because Python seems to be easy way of.
Yeah, I mean, I guess you could write the bytecode by hand as well. Would be a terrible, terrible, awful job, but theoretically possible.
All right, thank you.
I can actually add to this answer. At the company I work for, we do compile eBPF programs and then move them around to different machines. And as long as the kernel is the same version, it works fine.
Okay.
You had a question, right?
Hi. There seems to be some overlap between this and Audit D.
Is there some overlap between?
Between this and Audit D.
I don't know enough about Audit D to answer that, I'm afraid.
Okay.
Sorry. Yeah.
Great. Thank you.
Yeah. All right.
Do we have? Oh, okay. One last question.
So you say that is you can write code in Python and Lua. What about Go?
And C++ as well, actually, I think BCC supports. Yeah.
But Go is no.
There is a project called Go, I think it's Go eBPF. It's another sister project in that IOVisor family of projects. I haven't tried it myself, but I believe it's, it describes itself as, under development or something, words to that effect. So yeah, I'm sure it is possible to write BPF programs that way, and I'm sure that will be something that becomes more and more prevalent, because we like Go in this community, right?
Cool. I think we're out of time. And if any more of you have questions, you can, I guess, catch up with Liz on the hallway track.
Definitely, yeah.
And let's give another round of applause. And
thank you very much.
yeah, thank you very much.